After studying this chapter, you should be able to understand the terms and operation of a closed-loop control system block diagram, describe the basic operation of on-off control systems, understand the concept and operation of a proportional control system, including bias, and calculate the error and controller output given the system gain and inputs. Understand the concept of deadband and calculate the deadband range for a proportional control system. Understand the concept and characteristics of integrated control. Understand the concept and characteristics of derivative control. Understand the concepts and characteristics of PID control. Explain the circuit operation of an analog controller. Explain the principles of operation of a digital controller, including programming concepts and sample rate. Understand the concept of stability and interpret a Bode plot. And implement two methods of tuning a process control system. Broadly speaking, control systems can be classified into two groups, open loop and closed loop. In an open loop system, no feedback is used, so the controller must independently determine what signal to send to the actuator. The trouble with this approach is that the controller never actually knows if the actuator did what it was supposed to do. In a closed-loop system, also known as a feedback control system, the output of the process is constantly monitored by a sensor. The sensor samples the system output and passes the information back to the controller. The controller can make any adjustments necessary to keep the output where it belongs, since it knows what the system is actually doing. This self-correcting feature of closed-loop control makes it preferable over open-loop control in many applications. In this chapter, we deal with the principles and hardware of closed-loop controllers. Clearly, the heart of the control system is the controller, an analog or digital circuit that accepts data from their sensors, makes a decision, and sends the appropriate commands to the actuator. In general, the controller is trying to keep the controlled variable, such as temperature, liquid level, position, or velocity, at a certain value called the set point, or SP. A feedback control system does this by looking at the error, E, signal, which is the difference between where the control variable is and where it should be. Based on the error signal, the controller decides the magnitude and the direction of the signal to the actuator. For a process control system, the job of the controller is to maintain a stationary set point despite disturbances. For example, maintaining a constant temperature in an oven, whether the door is open or closed. Often, in a process control system, the set point is established by another controller acting in a supervisory role. In a servo mechanism, the job of the controller is to have the controlled variable track a moving set point, for example, moving a robot arm from one position to another. Engineers approach the problem of designing a controller for a servo mechanism differently than they would for an industrial process control system. For a servo mechanism such as a robot, the transfer functions of the individual system components are usually known or can be calculated. For example, the transfer functions of motors and sensors are usually provided by the manufacturer. The transfer function of mechanical components can be calculated based on the laws of physics, for example, the moment of inertia, and empirical data. The response of the servo mechanism can be modeled using higher mathematics, and the precise characteristics of the controller are then determined. On the other hand, for a large process control system, so many factors affect the system performance that engineers take a more empirical approach. This means that they use a general-purpose controller and then tune it to meet the specifications of a particular system.